That should be in here. Let's see, make sure it's somewhere around there, and it should be somewhere around here. Okay. All right. Now that you've ruminated, normal force. Where? What?
Upward on the void.
Okay.
And downward on the void.
Yes, that's the force that he exerts on the board. So I have this normal force going up, normal force going down. Now, if you've read the book, you might look at that and go, well, this problem is it's a lot simpler than we're making it. Right, I'm just trying to connect some of the stuff that we've done before. We are taking the long route, the long path to get this. We are assuming it's all in equilibrium. Which means what?
So
net force
zero,
equal
change in velocity is zero.
And
net force equals 0.
yes, and that's the one that applies directly to what we're dealing with right now. We've got those three conditions. So the net force equals 0. So if he's in equilibrium, he has two forces acting on him. We have this normal force holding him up and this weight trying to pull him down. They have to balance out. In other words, if I drew it, when you add vectors, you add them head to tail. We have normal force acting up. And now I'm here. And then weight acting down. And we should end up back where we started. If it's an equilibrium, when I add the forces, we end up back where we started. Because the resultant is from where we start to where we end. And so, in essence, what I'm saying is that the magnitude of the normal force must equal the magnitude of the weight. Thus, when you're standing on a scale, the scale is really measuring normal force, but if you are in equilibrium, the value should be equal to your weight. But how do we find the weight of the person? I know his mass, but how do you find weight? Well, we're in luck. Unless you're using an audio reader, then you're not in luck. There is it's known as Newton's second law. The fact that force and acceleration are proportional, with mass being the constant of proportionality. This is what I consider the most important formula in all of physics. It is something that we will visit again and again. So this is the total force is equal to the mass times the acceleration of an object. Now, this is a chapter 4 thing, but it does come in handy when we're talking about how to find the weight of an object. So if I have an object in free fall, for those who need the visual, while it is falling, what are all the forces acting on it? Bless you. We did this one already. Force diagram of object in free fall.
Just wait.
Will you stop in there?
Would you have weight acting up?
On the ground. Okay. Any other forces acting on the ball?
Gravity. Gravity.
That would be weight. Okay. So in the case of something falling, the net total force is its weight. And the acceleration of an object in free fall is known as the acceleration due to gravity. This little g right here equals acceleration due to gravity. It is not a constant, but we often treat it as such. Not constant, but close enough if change in the height is small. And what I mean by small is, if you think about the size of the Earth, small compared to the size of the Earth. The value of G at the top of the Empire State Building is close enough to the value of G at the bottom of the Empire State Building. So we consider for things that are, within a couple miles of the Earth's surface, it's constant, close enough. Anyone happen to know what the average value is near the surface of the Earth?
Was it 9.8?
Do you know units?
I can't remember that. I just remember in the book what the number was.
All right, 9.8 is the number if you're dealing with metric. 9.8 meters per second squared. Instead of an equal sign there, I should put the squiggly one. It's approximately equal to G. So if you see 9.8 meters per second squared, they're probably talking about acceleration due to gravity on Earth. Hewitt oftentimes just rounds it off to 10, just to make the math easier. Now I want to emphasize the fact that it is not constant. G, for Winston-Salem, 9.798 meters per second squared. There have been two major studies to try to find the acceleration due to gravity throughout actually the world. The first one actually might have just been the US. The more recent one was done by, they flew a plane with a sensitive equipment all over the US. They basically had a grid pattern, and so they found acceleration due to gravity that way. And then in the 70s, I believe it was, they planted various instruments throughout the country. And the one in Winston-Salem, one of the ones in Winston-Salem, is there's this road right out here that tees into Silas Creek. In the median, right where that road sort of hits, they had the spike right there, which is about this level, 9.798. If you are in, I think Rome is 9.800, and so it varies depending upon where you are in the world. So in a lab, in the labs, if you can see 9.798, or if I haven't corrected it, 9.796, I made a mistake the first time I did it, so a lot of labs, I'm slowly changing those. But if you see this is because this is true for Winston-Salem. So, over here, we assume this is some generic place on Earth. And so the weight of the person is going to be the mass, 100 kilograms, times generic value Now, my comment that you're not necessarily in luck if you're using an audio reader is because all the readers that I have heard, when they get to mg, they read that as milligrams and not mass times acceleration due to gravity, which is a real detriment to any physics textbook, because every physics textbook is going to have mg in there somewhere, not meaning milligrams. I was looking at audiobooks at one point and had access to it, and basically told one representative that was a deal breaker. There's no way I would endorse any book that misread that. All right, so do the math. So it'll be 980. And then units. Well, I have units of kilograms and units of meters per second squared, and they're multiplied. So it would make sense that is a kilogram times meter per second squared. You treat units, when you multiply units, it's just like anything you're multiplying, it's just 1 times the next thing. And the kilogram meter per second squared is too much for physicists to write. That is a Newton. So by definition, and we'll put it up in, I guess this corner is a little bit more centrally located, 1 Newton. I have 3 lines there. When you see the equal sign with 3 lines, that means it is true by definition. There's no derivation, there's no interpretation. It is the powers that be sat down and they said, we are going to say 1 Newton is a kilogram meter per second squared. So we now have his weight, which is 980 newtons, and therefore the normal force is 980 newtons, which means this normal force here is 980 newtons. What is the weight of the board?
50 kilograms?
Ooh,
Oh.
I'm definitely going to say no to that, very vehemently, no. Now, some students I've done that to suddenly shrivel and never speak much anymore, but I do want to emphasize, this is a mass. Despite what the biology instructors tell you, and the life sciences people, where I've heard them say a weight in kilograms, and I cringe. In physics, we cannot make the assumptions that the biology people do. We are not limited to life on Earth. The universe is our playground. How would you find the weight of the board?
The same way you found the weight of a person.
Which is?
You want total 900, that's 980 newtons.
That was for the person. What is it for the board?
Well, it would be half of what the person was.
Okay.
So 490.
Yes. Plug it into the exact same formula. The weight of the board would be 50 times 9.8, which is 490. All right, questions here before I erase? Probably the stuff on this side.
I was just wondering about the tension on the ropes. Why you only draw it one way and you don't have to draw it like from the...
Draw the other one?
Yeah.
Generally, when you get into the meat of a problem, you realize there's some things that really are not particularly of importance. So if we actually did, I'm going to quickly go through if we did the full thing. So I have some sort of board here. This is attached to a ceiling up above it. I have a person standing on the board. This is attached to, let's say it's part of a building, and then I have ground down here. So I think this is self-contained at this point. If I did the force diagram, I have the board, I have the rope, I have the person, I have whatever this top structure is, I have 2 walls, and I have the ground. Actually, we could treat that as a building, and then I have the ground. So what I really care about is just the board. That's the main thing. But we have a tension acting up here. We have a tension acting down here. We have a tension acting up here. We have a tension acting down here. We have some tension acting here, tension acting here, tension acting here, tension acting here. We have a weight of the building. weight of, I'll just ask for structure, weight of structure, weight of board, weight of board, weight of person, normal force up, normal force down, and, normal force up on structure, normal force down on ground. All right. So if we did the whole self-contained thing, it would look something like that. I might have left something off, but that's hopefully the gist of it.
Okay, thank you.
And ultimately, all I still care about is just that. Part of it, as you get to more complex problems, part of the experience aspect of it is you learn to go, oh, I know I can ignore that. So sorry to change you. I was just hoping to
Okay, thank you.
cut out some of the extra. Any other questions at the moment? All right, so let's clean up our forces acting on the board there. Let's see if we have a dark enough color. So I have that 600 up on the left. I have 490 acting down in the middle. I have this 980 newtons coming from the person, and then I have some tension acting up here. Because ultimately I have the four forces acting on the board. The board is in equilibrium, so the total force better be 0, which means the total forces up must equal the total forces down. From an addition point of view, sorry, voice changing, I go down 980 newtons, because again, it doesn't matter which one I start with. I then go down another 490 newtons. Then I'm going up 600 newtons. And since I'm going to end up where I started, because again, the total force is 0, so I better end up where I started, that's the tension we're trying to find. That's our unknown. Ultimately, if it's in equilibrium, the forces in one direction must equal all the forces in the other direction, magnitude-wise. Obviously, the direction will not be the same. So doing the fancy math here, 1470, going down. Therefore, 1470 must be holding it up. 600 have already been accounted for. So this has to be 870 newtons. So I've done my math right. 600 plus 870 is equal to 1470. Questions? We were about to wrap up chapter 2. We're getting close to it. I'll leave that up there. Oh, having trouble
No,
reading?
I'm talking to myself, sorry.
Okay. It looked like you're trying to see that stuff and not the stuff I just erased. I should have
I am.
asked.
I got myself there.
If you miss the stuff on this side, it's still here. Actually, it should be recorded. centuries from now, people will be able to look back on this moment. What are the backups YouTube has? Are they just one small glitch away from everything being lost? I know I've asked this already today, but we'll do it again. What are the three things that tell me that something's in equilibrium? And wait, before, and without looking at your notes, how many can you get? Three meanings of equilibrium. I wasn't expecting you to be stumped on all three of them.
No change in velocity.
All right. There's one. Okay, look at your notes if you have to.
Natural force equals wind.
Two issues with that. One, that's not a general condition for equilibrium. That just happened to be true for that one case, and it's normal, not natural.
I'm sorry.
At this point, when people say natural force, I know what they mean. However,
Acceleration is zero.
yep, there's another one. And the third one.
Friction is equal to zero?
Not friction. Yeah. Force. Total force. Net force. That's sort of right there. All right. Again, if one of these is true, the other two are true. So if I have an object that is moving along, let's just make it middle of space. There's nothing there except for this one object, so I'm not worrying about any other forces. It's cruising along at 50 meters a second. At what point will it stop? The only way that you can have a change in velocity is if the net force is not zero. Things will keep doing whatever they're doing until some net force acts on them, non-zero net force acts on them. This property to want to continue doing whatever you're doing is known as inertia. Inertia is a concept, first off. The tendency of an object to maintain constant velocity several ways to word it, until an outside, I guess I should put some clarifiers, a net non-zero force acts on it. And really what he is saying is that objects want, as a natural tendency, they want to do whatever they're doing. Which brings me to my biggest issue with Hewitt. Ugh. every time. When they went to the new edition, to the 12th edition, I thought, oh, maybe they changed it. Over here in a bubble on page 26, Hewitt uses the unfortunate terminology. You can think of inertia as another word for laziness, parenthetically, or resistance to change. I'll agree with the resistance to change, but that's not laziness. If I'm out digging a hole, if I'm lazy, I want to stop digging as fast as possible. Resistance to change is once I start digging the hole, I want to keep digging it. I don't want to stop once I start. Now, I don't want to start to begin with if I'm not doing it, but once I start it, that's what I'm going to keep doing. And for the next bit, I did get my daughter's permission to use this. Except when I had her in class, she did not want me to use it during that time, but other than that, she was okay with it. But growing up, my wife and I called our daughter Inertia Girl. Because she'd be at home, we have to go to the store, she'd be too young, we couldn't leave her. Despite Romulus and Remus's success being raised by wolves, we did not want to leave our daughter being raised by the dogs. So we need to go to the store, we want to take her with us. She didn't want to go. So we get her into the car, we get to the store, she doesn't want to get out of the car. We get her into the store, it's time to leave, she doesn't want to leave the store. We get her into the car, get home, we go inside, she's staying in the car. Whatever she was doing, she wanted to keep doing. Now, how much of it was because she was a redhead, I don't know, but that's the little girl that I still picture in my mind, even though she's married and she just made a successful bid on a house. But I still picture her this big. Sorry, it's going to get a little teary there. All right, physics. So inertia has the tendency to want to keep doing whatever you're doing. Newton summed this up in Latin, so I won't do the Latin part. In a much wordier version, I'm assuming that most of you have heard this before, an object in motion, and I'll try spelling correctly, an object in motion stays in motion. Now, I'll parenthetically add, at a constant speed and direction. Unless acted upon by a net non-zero force. And the other part of that is, some reason it generally gets split out. An object at rest, stays at rest, unless acted upon by a net non-zero force. This is a huge departure from the ancient Greek philosophy.
Which law is this of Newton? Which law is this of Newton?
This is Newton's first law. Newton's first law of motion. He also has laws of planetary motion. This is Newton's first law of motion, which is abbreviated, I will abbreviate it as N1, it's supposed to be a 1 there, N1L, Newton's first law. Now, I'm not quite sure why he bothered writing Newton's first law, because Newton's second law covers this. Just Newton's second law is the math version of this. So if I take an object, and we'll just take this box right here, and I push on it on the table, Question is, why does it stop? The ancient Greek belief, the belief that was in place for 2,000 years, was that it stopped because it wanted to be at rest. Newton comes along, and he is standing on the shoulder of giants, but Newton comes along and summarizes it all, and basically says it stops because something forces it to stop. If that friction were not there, it would just keep going until some other force acted on it. But the natural tendency is to want to keep doing whatever it was already doing. Because of the connection here, Newton's first law sometimes is just referred to as the law of inertia. So, since inertia is a concept, how do you know which objects have more inertia than others? I think I'm safe on this one. Do I have more inertia than any of you, or do you have more inertia than I have? Or is it the same? Kind of like there was a question mark in that answer.
Would it be higher if you're actually in motion?
No, the tendency is going to be the same. The amount of, let me circle back to that one. There's some other things I want to bring in first. All right. So think about it this way. You put an elephant on roller skates in the hallway. And then you put just an ordinary dog on roller skates. And I'm doing roller skates just to minimize the friction. You push on both of them. Which do you think is going to change what it's doing more?
No.
Why?
The small.
All right.
That's way
Almost there.
mass.
Somebody just said it?
Mass.
Yes, less mass. Now, the mass and the weight are related to each other, and the mass is related to the size because their densities are roughly the same. However, specifically, it is the mass. So the quantification of inertia, the thing which tells us what has more inertia, is the mass. So mass is quantification, because I can't think of a better word right now. It's the number which tells you which has more inertia. A couple years ago, there was this big to-do in physics about the Higgs boson. The Higgs boson is supposed to be an explanation for why this is true.